Okay, so today we're going to be answering the question about what happens with equivalent resistances and total resistances in parallel circuits. So earlier this week, you all did your investigation to see what adds up in parallel circuits, and you found that our resistors don't add up in a simple way, not like they did in series circuits. So, for example, in this circuit that we were working with yesterday, this 2 ohm and 4 ohm resistor would not give a total resistance of 6 ohms in this parallel circuit, not effectively anyway. So before I show how to calculate that equivalent resistance, I would like to take a second to record our total current in the circuit. So along this red path through R1, this I1 current traveling through that was 4.5 amps, and the current traveling through R2, or I labeled it here I2, was 2.25 amps. And so that tells me that the total current in this circuit, right, what would enter that sort of junction point and what's coming out of the battery here is whatever the sum of these two things is. Because whatever's coming in, however many electrons per second are entering this junction point, have to be the same as what's leaving that. So our 4.5 and 2.25 would give a total current in this system of 6.75 amps. That's what's coming out of the battery. And I just want to record that because when we calculate our total resistance, our equivalent total resistance, we should be able to use our voltage and that resistance to get this exact same current. So let's go over that messy equation to calculate total resistance in a parallel circuit. That is that the reciprocal, and the annoying part about this is that we are dealing with a lot of fractions, a lot of reciprocals. Reciprocals mean 1 over whatever that is. 1 over our total resistance, so this is a sloppily written TOT for our total resistance, is equal to 1 over the first resistance plus our second resistance plus, and then as many resistors as we have in this parallel circuit. Now, when we plug this in, and I'll plug these numbers in here, I would advise you to be careful with just like how you plug this in the calculator. Of course, calculations get more complicated when we have all of these fractions, all these divisions, reciprocals floating around. So I'll show how I would tend to type this into a calculator, and to especially be careful if you're using like a scientific calculator or your phone, which I will be here. Just be careful because order of operations can get weird when you're plugging in these reciprocals. So let's try that here. So I don't know what the total resistance is. That's what I'm trying to calculate. So I'll just leave that as 1 over our R total. And we have R1 as 2 ohms plus 1 over 4. And I'm going to take a quick aside. I'm just going to show down here how I would plug this into my calculator. So I wouldn't even do anything with this 1 over R total. That's symbolic. We're not going to plug that into our calculator. But I would take 1 divided by 2 and make sure that you use parentheses. The only reason that I say to make sure is because that way you don't end up like accidentally adding 1 then dividing by 4. Like if you hit enter at any intermediate steps, it'll throw off your calculation. So I would say it's a good idea to keep things in parentheses. So 1 divided by 2, all in parentheses, plus, and then another parentheses, 1 divided by 4, and that way you'll get the right answer. And I know that 1 over 2 is the same as 0.5 plus, and then 1/4 should just be 0.25. Boy, I really ran out of room over here. But 1/2 plus 1/4, or 0.5 plus 0.25 should just give us 0.75 or 0.75. Now that's not our final answer yet. That is 1 over our total resistance. So if I want to know what this actual total resistance is, I need to take the reciprocal of both sides. So I want to basically flip both sides of this equation. So now our total resistance should be equal to 1 over 0.75. I added an extra 0 there, just 0.75. And we should get something like 1.33 repeating. And that many ohms is our equivalent total resistance. One thing to notice, that's actually lower than both of the resistances individually of these two resistors. That's lower than 2 or 4 ohms for our total resistance. Now, we recorded what this total current was in our circuit. Let's see if we still get that total current by taking Ohm's law, so V equals IR, and our data that we have now. So let's see if we plug in our total voltage. So our battery is a 9-volt battery. We have some current that we're trying to solve for. I'm going to write that in green so we can see more easily if it matches. Times this 1.33 ohm total resistance. That's the sort of sum of the reciprocals and then inverted of each of our resistors. And then if we're trying to solve for this current, this green I down here, we've got to get rid of whatever's next to it. So we want to isolate our I. Right now, 1.33 is being multiplied by I. So to get rid of this 1.33, we have to divide both sides by that. And if we do 9 divided by 1.33 and we hold as many 3's as we can, we should get the exact same thing that we got before. So we should get that that current is 6.75 amps. And so we can confirm, and one of the questions on this asks you to just sort of confirm or check. You can show that in a lot of different ways, but check that your current is the same from your total resistance and from your voltage as what you would have predicted based on these individual currents being added together like they do based on off Kirchhoff's law.